So is there a place where we could put these particles where they would stay in the atmosphere a long time, so we don't have to dump billions of tons into the atmosphere, and where they're far away from people so they don't kill us? This seems to be what volcanoes do. So to understand what volcanoes do and how we might duplicate it, we have to understand convection and the stratosphere in our atmosphere. So hopefully you're familiar with convection. The basic idea is that if you, for example, take this ground over here on this side of a building and heat it up by having sunlight falling on it, the air nearby will get hot, and therefore drop in density and therefore rise, and this will cause a flow of air. Meanwhile, cold air will come down to replace it. And this is convection. And you can see I've heated up this side of the building and the ground on this side from the sunlight, and it's causing a flow of hot air upwards and occasional bubbles of hot air boiling up. Meanwhile, cold air is sucked in at the bottom. And this is a very common phenomenon whereby air or water or other fluids move around under the influence of heating. Okay, so that's convection. Another clue is that when you go higher in the world, the temperature drops. You can see the tops of mountains are covered in snow, while the bottoms of mountains are often not. So somehow it gets colder as you go up. Typically, the temperature drops by about 6 degrees centigrade for every kilometre you go up. So you're 1 kilometre up, you're 6 degrees colder than you are at sea level. Why does it get colder as you go up? Well, it's a combination of two things. First of all, the sunlight tends to hit the ground, and so the ground is where the heat is injected into the system. Sunlight is not absorbed so much in the atmosphere, at least the lower atmosphere. So most of the heating from the sun is at the bottom. So just like a cooking pan, the heat's at the bottom. And it gets colder when you go away from the bottom. But the other reason is convection, that the air moves up and down, and as it moves up, as we've been talking about, it expands and therefore cools down. So the motion of the air once again causes the air to be warmer at the bottom and colder as you go up. Now remember, we talked earlier about lapse rates. If you have dry air and you raise it, it'll cool down like this in a diagram of temperature versus height. This is the dry adiabatic lapse rate. If it's got lots of water, it will start off going like that until it reaches saturation. At that point a cloud forms, droplets condense out, and now it cools down at a more gentle rate as it continues to rise. So it's 10 degrees C per kilometre for the dry rate, and somewhere between 2 and 8 degrees C per kilometre for the wet rate. Okay, so let's put this together. Okay, so let's imagine we have an atmosphere and it's got the environmental lapse rate, which is about 6 degrees per kilometre. So that's what the air is normally doing. It varies a lot from day to day and depending on the weather, but something like that. Now let's imagine sunshine hits the ground underneath and it heats up some of the air right at the bottom. So the air that starts off at this temperature gets heated up over to here. Now because it's hotter than the surrounding air, it will have a lower density. And because it has a lower density, it will have a buoyancy force that will cause it to rise. So this air will rise. But as it rises, it's dry air, so it'll cool down according to the adiabatic lapse rate, which is about 10 degrees C per kilometre. So that's faster than the surrounding air. So as it goes up, it'll cool down, until eventually at some altitude it will reach the same temperature as the surrounding air. And at this point it will stop rising because it's got the same temperature and therefore the same density, so there's no more buoyancy force, so it'll stop rising. So you only get convection when the air is hotter than the surrounding air, which normally limits the thermals, so they don't go up too high. These are called thermals, the air rising on a hot summer's day off the ground, and they go to a certain height, but not all the way. Of course, their motion could stir up the air above and cause that to move us around, so it's going to stir up all the air, but you're not going to get massive instability. Okay, but now let's imagine instead of doing this over a desert, we're doing this over a tropical ocean. So the air has got lots of water vapour. And once again the sunlight beats down and heats up the air near the surface, and it starts to rise. Now we saw before that it went up at the dry adiabatic rate until it intersected the blue line, and then it would stop rising. But now let's imagine as it rises, Before it reaches the surrounding air temperature, the blue line, let's imagine it gets saturated. The water's going to start condensing out, at which point it will now continue to cool at the wet adiabatic lapse rate, because the water is condensing out, releasing its enormous latent heat. And so this means it can continue to rise and it will not stop convecting. In fact, it will go faster and faster and you get a really strong updraft. And this is what creates thunderstorms. They only happen when there's hot, moist air, because they need this wet adiabatic lapse rate to allow the convection to keep going for a long time. And you get this very rapid updraft producing these big thunderstorms. And this is what creates hurricanes, cyclones. It drives the entire world's circulation. Okay, so that's convection. You need something that does not intersect the surrounding air's temperature and environmental lapse rate. But what you sometimes get is what is called a temperature inversion. Normally, as we said, as you go up, it gets colder. But just occasionally, as you get up, it goes hotter. And this is what a temperature inversion means. Inversion means it's the opposite of normal. Now, the main way this happens is on cold, clear nights. It happens regularly in Canberra on cold, clear nights. The ground is now radiating infrared radiation out to space and cooling down really fast. So the ground can be much colder than the air. The air near the ground loses heat to the ground and also gets cold. So what you get is a thin layer near the Earth's surface, maybe 50 or 100 meters thick, which is cold. And then when you're further up, you're 1, 2, 3 kilometers up in the atmosphere, normal behavior resumes and the temperature drops as you go up. So this is called the temperature inversion. And it's important because of what it does to convection. Now let's imagine it's morning, the sun is starting to shine, and some of the air at the ground is heated up. It won't go very far, because as it goes up, it will very rapidly hit this blue line. So what this means is when you have a temperature inversion, it locks the convection. It stops the convection getting up very far. Even if you had incredibly humid air, which you often do on foggy mornings, it's not going to help, because even a wet adiabatic rate is going to hit this blue line very quickly, because the blue line is slanting to the right, whereas any air that's rising is going to be slanting to the left. So you get this often in Canberra. Here's a picture I took at Mount Stromlo Observatory showing a temperature inversion in one morning. There's lots of fog locked below the summit of the mountain. So there's convection starting up here, but it can't get very high, even though it's foggy, so it's clearly saturated. It's full of water, but it still can't rise very far because the temperature at the surface is colder than the temperature at this sort of altitude. This is classic temperature inversion. It's really bad for pollution. This is a picture, I think, of Alma Ata. But what you can see is a temperature inversion here, and that's locking the pollution, the smog, below the nice clear air further up. So temperature inversions, whenever you get the temperature that goes up with altitude rather than going down, that stops convection. Convection can't carry the stuff away, and that's going to be really crucial.